So good morning and welcome back. Welcome to the final lecture of this course. Today we'll turn to classical mechanics again. And we already had on a problem sheet some classical mechanics. I'll very quickly review this. And then we'll come to the topic of kinematical and dynamical symmetries and a distinction from the point of view of the cotangent bundle. And then should give you some insight into the Runge-Lenz vector and what the difference is to the kinematical symmetry generators you have, say, on flat space, like rotational operators and so on, generated by the angular momentum and other observables. And so we'll start with 6.3, kinematical and dynamical symmetries. So you see this is the third lecture that's totally concerned with physics, so that raises the proportion of physics in this course to an unseen 11%. I wish you to notice this. Okay. So let's recall from one of the previous problem sheets the setup of classical mechanics in a symplectic manifold picture. So we have the definition that a 2n dimensional manifold, smooth manifold M, together with a two-form omega, with an omega which is a two-form on this 2n dimensional smooth manifold, for which the following holds. A, this two-form is closed, so that means that the exterior derivative of the two-form is 0. And the second condition is that the two-form be non-degenerate. So this is closed. And non-degeneracy here means that if you have omega comma x equals 0 for all y, well, what is y? Y is a vector field, obviously, on this manifold. Then you can already conclude that x is 0. Okay, and that's a non-degeneracy condition. And such a pair, M with omega, satisfying these conditions, is called a symplectic manifold. It's a symplectic manifold. And on a symplectic manifold, we have observables, and those are simply the smooth functions. Observables are the smooth functions on this 2n dimensional symplectic manifold. Now, this makes contact with what we know from classical mechanics via the theorem that there always exist Darboux coordinates in an extended region. So theorem, for any point of this symplectic manifold M, there exists an open set U containing P, so it's not the empty set, containing the point in question, such that there also exist coordinates. So, yeah. Let's call them psi. I know you hate it, but let's call them psi. So there are coordinates from U into R 2n. Why? Because it's 2n dimensional. Such that if we consider the omega, this symplectic form, as it is called, in the thus induced coordinate system. So this is the psi. Let's write capital A, comma, psi capital B. So I label from A to B, AB from 1 to 2n. I label the coordinate-induced tangent vectors such that this guy, and that's the statement of the theorem, there exist coordinates on such an extended region such that the omega looks like this. And all the remaining entries are 0. And I indicated here 2 blocks where each block has the size n. So in total, this is a 2n by 2n matrix. Okay? And note, this is very special because it's not just a normal form for an antisymmetric 2n by 2n matrix at one point. It claims that on the entire, that around a point there's always an open region, maybe a small open region, but it's nevertheless an open region, where on the open region you can extendedly choose coordinates, and nevertheless over the entire region the omega takes the simple form. Okay? For metric manifold, that's not possible. You could do this at a point, but not in an extended region. And whenever there is a coordinate system in an extended region such that the geometric structure you have, well, that's a tensor field you equip this guy with, has constant components with respect to a coordinate system, then we call the manifold flat. So one statement here could be a symplectic manifold is locally always flat. Right? So, okay, that's this. And these coordinates here, they're called Darboux coordinates. So the psi, well, yeah, the psi that goes from U to R2D, such psi are called Darboux coordinates. Okay? Fine. And it's convenient to split them into 2 parts. One half of them you call Q, and the other half of them you choose to call P, the coordinates, such that the Darboux coordinates are the Q1 to Qn, and then the P1 to Pn. Okay, and we agree to label those up and those down, and this is just a convention, but obviously by now you have a feeling for why we would like to do that. Okay, so the usual QP split has to do with having these Darboux coordinates. This is just a name for these 2 different parts of the coordinates, right? So once we did that, we can immediately find that if the omega looks like this, then we can define an omega carpet. It's like the musical symbol. You raise the indices. You do this. It's the inverse. So we define this guy in Darboux coordinates AB, such that omega BC equals delta AC. Now, you can do this always. Why can you do this? Well, because it's non-degenerate. This condition tells you that in any coordinates you could do this pointwise. And in Darboux coordinates, whose existence the theorem guarantees, we find that omega sharp, which now has indices up in Darboux coordinates, is given by this guy, but now the minus, the identity is down here, and so the minus flips down there for obvious reasons. Okay, so that's quite useful to keep in mind, because that's exactly the minus sign from the Hamilton equations. Well, I didn't tell you that yet. Well, I did, but forget about it for a moment again. Because we now have another definition, namely that of a Hamiltonian vector field. It's a little bit of a misnomer because the Hamiltonian vector field exists for every observable, not only for the Hamiltonian. Okay, let F be an observable. So a smooth function on the symplectic manifold. Then we define the Hamiltonian vector field. Again, it has nothing to do with the Hamiltonian. The Hamiltonian vector field, let's give it a name, capital X sub F, with respect to the observable F, that's the full name, as the vector field, xf, well, as omega x comma open slot. This vector field, this is a 2 form on the big manifold, so the resulting object is a 1 form, right? And you require this to be the exterior derivative of the observable, but the observable is a function, so it's a 0 form, so this is a 1 form. 1 form on the symplectic manifold equals 1 form on the symplectic manifold. That works. Why does this, sorry, this is x down f. This is so, it's a little implicit, the definition of xf. Well, we can of course write it equivalently. This is xf equals omega sharp, which can eat 1 forms. And so this is in the dual of the dual, this is in the vector space again. Okay? And so this xf is the Hamiltonian vector field associated with the observable. Now this is an excessively geometric concept, so we'll draw a picture. Picture. So let's do this for 2n equals 2 dimensions. So if we go to Darboux coordinates, we can certainly look at the chart, okay? Where here I got the q's and there I got the p's. So you see I use q's and p's. So obviously this is not a picture of the manifold, it's a chart, okay? And maybe this part of the chart is the image of the Darboux coordinates. Okay, so what's in here? What's in here is the image of Darboux coordinates, and there may be some funny looking a sphere, for instance. Yes, sphere, yeah, a sphere, for instance, right? Okay, and so this is just, this is the bit u, and this is mapped by Darboux coordinates to a part of this R2n. Okay, so we have this, and now assume we have an observable f. So an observable, what is an observable? An observable is a smooth function on this manifold. So in particular, I can look at the level sets. I can ask for any real number c, what are all the points capital X in R2n, such that f, well, in these coordinates in this chart, no, anywhere, but I represent it in the chart, has constant value c. And for instance, the f could have level sets. All right? That could be the level sets. And let's say this is 1, this is 2, this is 5, something like that. Now, let's construct the Hamiltonian vector field that corresponds to an observable with such a level set. So here, obviously, what we need to do, we need to calculate the exterior derivative of the function. But the exterior derivative of a function is simply the gradient, right? It's a partial derivative in all the directions. And that we know that there will be a gradient at every point being orthogonal. Well, actually, this is smaller, and this is longer, and this is much longer. So there is a gradient at every point, right? So this gives rise to an immediate vector field, df. Well, it's a covector field. I'm sorry. It's a covector field, and I nevertheless indicate it by arrows. Okay, so forgive me. Okay, so now we take this covector field, and now we apply this map to it. What does that mean? Well, if you think in matrices, if you think in components, you apply this matrix to it. Are you confused or something wrong? It's not a vector. It's yeah. Okay. It's clear what I mean, right? I mean, it's the f hat. It's the coordinate representation. Yeah. Well, this okay. So it's not a vector, so I make it a very big X. Now it's the coordinate representation of that function. So you have u goes to R2n, and from u, certainly if we have a function on M, we have a function on u. That's f that goes to R, and this is chi, and then f hat I wrote down is confused. No. Yes, this is yeah, f after chi inverse, right? Okay. Good. Sorry. Yeah. Well, but it's clear what it means. So the covector field, I apply to it this matrix. Okay. And what does that mean? Well, assume our covector field has components alpha and beta in the q and in the p direction, and then I act with this guy on it. What I get is, of course, beta and minus alpha. So that means the resulting vector field, now it's really a vector field, the resulting vector field actually is the y component of this one. So let's take this one. This has a y component which goes like up here, and that will be the x component of the vector field, and it has an x component that will be the minus y component. Okay? So what this will produce is an x component. Okay, let me go to this point. This is clearer. Okay, so it has an x component and a y component, our covector field. So this is the alpha and the beta, or a q and a p component. But the resulting bit is a beta. So this guy goes to here, and the minus alpha. That guy goes to there, so that will sit like this. And if you think about it, what this will simply produce is that the resulting covector, so the orange ones are the df's, but you will always flip them to vectors that are then tangent to the level set, very obviously. Because if you plug in something here that's tangent to the level set, right, it will be annihilated. So that means if you understand the level sets and the gradient field, you flip these guys in a certain direction. Had the one had been at the other side, it would, if we had the minus up here, like we have in the omega, but this is the omega sharp. If the minus had been up here instead of here, it would be overall minus sign. They would point in the other direction. So the question is, did I do it right? Is this really the sharp we want? The answer is yes, because, for instance, you could do this for the Hamiltonian. Okay? If you had the Hamiltonian, this is a little bit like a deformed oscillator, not quite harmonic, but okay. But then you would see, I have positive momentum, and the positive moment, well, it's a bad Hamiltonian, right? So let's do this for a Hamiltonian for the oscillator, okay? So the Hamiltonian for the oscillator would have this Hamiltonian, this DH covector field, but it would become this XH vector field. And you see, really, these were the P's and these are the Q's. For positive P's, the momentum brings me to larger Q's. A positive momentum brings me to larger Q's. From here on, negative P brings me to smaller Q's. That makes sense. Okay, so it really runs this way around. Okay, if this is P and this is Q, it must run this way around, and this is why the signs need to be like this. Okay. Anyway, if you have an observable, you draw the level lines, you calculate the gradient, and you flip it like this with the omega sharp, and the yellow thing is the Hamiltonian vector field. So with respect to that observable. So you see, it may look funny or abstract in the definition. It's something extremely intuitive. Okay. Right, so that's the Hamiltonian vector field. And once we have that, we can, of course, define the familiar Poisson bracket. And note, in order to do this, in order to have the omega sharp, we needed the non-degeneracy condition of the omega. We haven't used the closedness condition yet, but that will become important in a second. So definition is, if f and g are observables, so smooth functions on the symplectic manifold, then we define a bilinear map from C infinity m cross C infinity m back to the observable C infinity m by virtue of letting Fg be the action of the Hamiltonian vector field of the first one acting on the second one. Okay? And because the Hamiltonian vector field is defined in terms of such an omega sharp, the omega sharp inherits its antisymmetry as a true form. Well, the omega sharp is a second rank contravariant tensor, but the omega is a true form. It inherits the antisymmetry such that if you now exchange f and g, it's minus gf. Okay, so this is the Poisson bracket. Poisson bracket. And the properties, so, well, theorem, but it's not much of a theorem. The properties are that Fg is minus Gf because of the omega symmetries. And the other property that's important for us at the moment is the Jacobi identity, Fgh plus, and you rotate those cyclically to the Jacobi identity is 0. But in order to prove this, you need to use that omega is closed. Okay? Otherwise, you don't get the Jacobi identity. So and then, obviously, if we equip all the smooth functions here with a Poisson bracket, we get a Lie algebra, because those are precisely the properties of an abstract Lie algebra. And there is actually a Lie algebra, so this is a twiddle, there's a Lie algebra isomorphism to the Hamiltonian vector fields, equipped with the differential geometric Lie bracket. And in fact, we have that the Hamiltonian vector field of the observable that you get as a Poisson bracket of 2 is nothing else but the commutator of the respective Hamiltonian vector fields. So it's the X itself, the X map that associates with every observable in C infinity m a vector field that is exactly this Lie algebra isomorphism, right? Yes. Okay, so that's this bit, and then there's, of course, the important definition of an observed conserved quantity. A dynamical system or a classical mechanical system is a triple of an m, an omega, and a distinguished observable H. So where these guys constitute a symplectic manifold, and this H here is some distinguished, that means you choose it, some distinguished observable. And that is then called the Hamiltonian. Okay. And if you have that, you can define the change of any other observable, f, hf. This then defines how the observable changes in time, so you can make the observables time dependent. Okay, so obviously, well, we did this in the statistical mechanics course. So far, there was no time dependence anywhere. Okay, so now obviously here you're thinking about an observable evaluated along a particular curve in the symplectic manifold, and this dot acts on this curve inside. Okay, so as written with what we wrote before, it makes no sense. It only makes sense with the understanding that what is written here is actually the f along a curve. Okay, and here you evaluate only after you took the bracket, you evaluate along the curve. Okay, so this is sometimes hidden in this notation, and that's good or bad as you wish, physics tradition, but you know all of this. I just indicate this here. Okay, and then we have the definition that a conserved quantity, a conserved observable or quantity, conserved, C, or let's call it Q, is an observable for which the Poisson bracket with the Hamiltonian is 0. You know all of this. Now, an important remark is the following. In classical mechanics, sometimes one defines the Liouville operator with respect to an observable, or anyway, it's the Poisson bracket of an observable, say the Hamiltonian. It doesn't need to be the Hamiltonian, it could be any other one, with an open slot. Obviously, this is a map that takes an observable into an observable linearly, because it's the observable I can plug in here. Okay? So these guys appear, for instance, if you write down the formal solution of this problem, you write it as e to the, if the h is time independent, e to the t times, and then this object, which then acts repeatedly, okay, and you expand the solution. Now, this is sometimes in classical mechanics called L sub h, like the Liouville operator, or d sub h, that reminds you more of a derivative, because it's precisely this. If you put in here a product, which you can do, then it will satisfy the Leibniz rule, the product rule for this product. Why? Well, because the Poisson bracket ultimately also defines the, satisfies the, what's it called? Which I said, the Jacobi identity. Okay, but what I want, the attention I want, where I want your attention is that this object, which is a little bit like, okay, you can plug something in, something comes out, what is it? Well, in Darboux coordinates, well, we don't need Darboux coordinates. I have any observable f, okay, I'll write any observable f here, f comma g, we defined this as xf acting on g. So what happens if you leave the G out, if you say open slot, well, it means open slot here. It means this object is the Hamiltonian vector field of that observable. So if you see this, you can understand it algebraically, but from now on you say, oh, Poisson bracket with an open slot here, this is precisely, if these are the level lines of the observable, then this is this vector field here. So this object is a vector field on the symplectic manifold. It's extremely useful to think of this guy this way. And then the exponentiation of that vector field is nothing but the differential geometric exponential map. That means it's the flow along this vector field. And now it's totally clear why exp of t x sub h, that's the flow as you flow along the Hamiltonian vector field of the Hamiltonian. We could also say it's the time development operator. Right? It tells you how the system moves. Isn't that crystal clear from this picture? Okay. Anyway, so these guys, and hence the Hamiltonian vector field is not an abstract thing, it's something extremely concrete. Questions so far? So this is the short version of classical mechanics in terms of this geometry. Now I would like to make an important distinction. Well, first of all, we have the Noether theorem. Yeah. Well, a corollary of all this is Noether's theorem. In Lagrangian mechanics, one often makes a point out of showing this in the most arcane way. But let's assume that there is a conserved quantity Q. Let's assume Q is a conserved quantity. Now, the proof of the Noether theorem is to make the incredibly complicated step that you switch the entries, picks up a minus sign, but because it's 0, it stays like this. End of proof. This is the Noether theorem. Why? What does it mean? Well, this means that Q is conserved under the flow of H. And this means that H is conserved under the flow of Q. Example. And that's Noether's theorem. If one observable is conserved with respect to the flow of the other, then the other also with respect to the flow of the one. Example, let's take H being 1 over 2m g I j p I p j in Darboux coordinates, okay? And the Gij in those coordinates is also constant throughout the Darboux chart, okay? So it's just the standard inner product. Now we can calculate H comma P. Okay, let's not make it too complicated. Let's do it in one dimension with our one-dimensional example. 1 over 2m, and this P is being squared. There is only one P. And now let's calculate H with P. It's obvious that this is 0. Right? We could go through the motions. And that means that P doesn't change in time. It means P dot, if I can consider a curve, is 0. It doesn't change in time. However, you can also see that H is P conserved, and I would like to write down what the P conservation means. So there is this associated Hamiltonian vector field. Well, very strictly speaking, the H is a function of the Q's and the P's. And very strictly speaking, I should introduce another observable, capital P, that is a function of the Q's and the P's and is defined as the P. And then, formally speaking, I'm allowed to plug them in. But it leads to the same result. Okay? Okay. So now I take the Hamiltonian vector field with respect to that observable, P here. And you know what it is. We go to Darboux coordinates. Why? Because we can. So we get here dp by d, yet now it's little p. There's usually an index, well now there isn't, d by dq minus dp capital by d little q d by dp. Aha, but the p is just, the capital P is just a small p, so this term goes out, that's 0, this term is 1, so this is d by dq. Aha, so capital P acting on h, being down here, being 0, as is obvious, that means nothing else but d by dq of h is 0. But if d by dq of h is 0, that means h doesn't depend on the position. In other words, it's translation invariant. Okay? But it's exactly this. So this is the Noether theorem. There is nothing else to it. In Poisson bracket notation, the Noether theorem is equivalent to the antisymmetry of the Poisson bracket. Now consider Hamiltonians of a special form. And that special form is that the Hamiltonian of Q and P be given as a kinetic part, but the kinetic energy part may also depend on the Q's. This is usually not done in flat space, in flat base space, but here we'll allow it, plus a potential energy part, which, however, we now require to depend only on Q. And so this should be a clear split. All the dependence on P goes into this kinetic part, okay, and all the remainder goes there. And now let's make it even more specific, so as a further restriction. We require, so there's an exclamation mark, we require that this be given by, or we require that this part be given by a bilinear form G ij that may depend on the Q. So before in the example we made this metric on the configuration space independent of the position in suitable coordinates. Now we no longer assume that such suitable coordinates exist. There will still be the Darboux coordinates, but it doesn't mean that on the Q space alone that these factors are independent of Q, that you can find coordinates. We'll allow this to be like this. Pi, Pj. So in other words, we'll have a quadratic kinetic term. And you can put a 1 over 2 in front and a 1 over 2m, where we just put a 1/2 in front. Okay? So mass is 1, or you absorb it, something like that. Okay? For our theoretical investigation. So we look at Hamiltonians that have this kinetic term. If you set this potential to 0, the Hamilton equations will yield the geodesic equation. The solutions, if you project them down to Q space, will be the geodesics with respect to the Riemannian manifold provided by this metric on the Q space, or the inverse metric. Okay? It's the straight lines in that space. However, we allow a potential. Okay. Now, this form is a form that comes up in standard classical mechanics. Okay? But also standard classical mechanics on the sphere or something like this, where you have a curved metric and so on. But from now on, we'll only talk about this, because then we can make the following definition. For such Hamiltonians, we may distinguish, or we distinguish, two types of symmetries. Two types of symmetries of H, but we now know that the symmetries of H are at the same time the conserved quantities. So the symmetries of H are the same as the conserved quantities, conserved observables, by Noether's theorem. Okay? We distinguish two types of symmetries Q of H. So because it's a symmetry anyway, H comma Q be 0. So this notation is more like Q is a conserved quantity. If I write the other way around, it's more like H has the symmetry Q, but we know it's the same thing. Okay, anyway, two types. The type A is the one where the push forward okay. I have to say more. We consider, okay, of the form on a symplectic manifold which arises as the cotangent bundle of a base space. I was talking about this because I said here the G is a metric on the Q space, right? On a space of Qs. But somehow I can't say what the space of Qs is on a symplectic manifold because I could choose different Darboux coordinates that keep the omega still constant of that type, and then I have another Q space, okay? But if I have M arise as the cotangent bundle of some Q, then I can require that Q with the G is a Riemannian manifold. So that is really the setting I look at. The symplectic manifold is the cotangent bundle of a Riemannian manifold, and I use the inverse of the metric on that Riemannian manifold to build this guy, and now I know where all the objects come from. Okay, so this is the special case, and obviously that is how you, if you come from Lagrangian mechanics, which happens on the tangent bundle, then you do a Legendre transformation, we had this on the problem sheet, and you arise here. Okay? So, now, we distinguish two types of symmetries. The symmetry type A is where the push forward of the Hamiltonian vector field X associated with the symmetry exists. And because it exists, and I can require that the Lie derivative of the metric on the manifold down here, you see what we're doing. If M has this structure, then of course I have from the cotangent bundle down to Q, I have the standard bundle projection. If the push forward of the Hamiltonian vector field with respect to the symmetry of H, A exists, and it's a killing vector of G, that means the Lie derivative with respect to it on the metric here, and that now of course lives down there, is 0. This is called a kinematical symmetry. Such the Q is called a kinematical symmetry. And B are all the other Qs. Let's go back. Why does the push forward of this field not necessarily exist? Well, we know that the pull back of a covector field always exists, right? But the the pullback of a vector anyway, and the push forward of a vector exists anyway. But the pullback of a covector field always exists as a covector field. But the push forward of a vector field doesn't necessarily exist. It only exists if the map is an isomorphism. But the pi is a projection that's not an isomorphism. Well, the picture to this is how this could not exist. So that's a picture to B. So e.g., if this is the Q, and I now have all the the cotangent fibers at the various points of Q, then this whole guy is, of course, the cotangent bundle. And now assume I have a vector field on this cotangent bundle that looks like this, and assume that under the projection map that takes me down here, this guy is mapped to, so this green guy, which could be the xq vector field. I can now take this individual vector and map it down here and say it's mapped to this vector. So say the blue one is the push forward of this green one up here, namely the one at this point here, so this particular vector. But what happens if this here is pushed forward to this tangent space at this point, but to a different vector, say to this one? Then you don't know which of these, you don't produce a well-defined vector field here because you have multiple images. That can happen, okay? We discussed this before. I think it caused some confusion before, but think of the push forward of a vector field not necessarily existing. Only if these conspire, if this field conspires along here in such a way that whatever value it takes here, the push forward is the same of the push forward of the value there. It's a very strong restriction, right? That they all coincide. And if this restriction is satisfied, then it exists. And then it's still not a kinematical symmetry. A symmetry it is anyway. Still not a kinematical symmetry. It also, the vector field down here, the blue one, needs then to be a killing vector field, namely the Lie derivative of the metric with respect to it vanishes on the manifold down here. Okay? And the killing vector fields are the generators by the exponential map of isometries on the base manifold, so transformations that don't change the metric down here. Okay. And all the other conserved quantities we find in classical mechanics, where, for instance, this guy doesn't even exist, and we don't need to check more, are called dynamical symmetries, are called dynamical symmetries. Okay, so let me point your attention to the fact that, okay, it needs to be a symmetry. So a symmetry it always is, but then the distinction, you see the distinction doesn't use the potential. It's a symmetry, it needs to push the right way, okay, fine, but that has nothing to do with this potential. And this only refers to the kinetic part here. And therefore we call it a kinematical symmetry because it only refers to the kinetic part. And there, and you see the kinetic part only refers, well, by construction, but that's essentially Newton's first axiom, that the kinetic part looks like this. Because if you don't have a potential, that means you don't have a force, particles are supposed to move along straight lines. Well, in order to get that, you could also take the square root. They would still move along straight lines. By not having the square root, you move along straight lines, and in equal times, you cover equal distances. That's what you say, you have a uniform straight motion. That's Newton's first axiom. In the absence of forces, you have uniform straight motion, and it's precisely encoded into here. And a kinematical symmetry is one that you have that refers to the geometry that you have without the forces. And all the others, therefore, obviously must have something to do with the potential. So if it's still a symmetry, they will depend on the particular type of potential you have, whether you have the symmetry or not. That's a dynamical symmetry. And that's how it's usually defined. And the examples, and after a break, we'll discuss this. So prototypical examples are for type A, for type A is, say, the angular momentum L, which is Q cross P. So this is obviously on n equals 3. This is in 3 space dimensions, so in 6-dimensional phase space, you can have this angular momentum. If you have a, say, flat metric, then that will be trivially a Killing vector field. Yeah, that is a Killing vector field down there. But you see the angular momentum is an observable QP. So what's a Killing vector field is the push forward of the Hamiltonian vector field with respect to the 3 components. So there are 3 conserved quantities here. That's this. And a prototypical example for type B is if you have a Hamiltonian. So this is certainly only if the Hamiltonian, say, is 1/2 Gij Pi Pj, and the Gij in the chosen coordinates is unit, right? Well, I shouldn't say unit. It's the Sylvester form. The other example is if you have 1/2 Gij Pi Pj, again flat metric, minus K, some gravitational constant with the central mass absorbed there, divided by the absolute value of Q times the unit vector of Q. Well, we could write here the square, and then again, hang on, now I'm confused. The potential, I'm sorry, the potential is just this. Yes, that's right. So that would be the Kepler potential. Okay. Then you have this object, which we call capital F. It's not the force, it's the Runge-Lenz vector. So because it has 3 components, we're not talking about 1 conserved quantity, we're talking about 3 conserved quantities. And you may remember that this is given as P cross angular momentum minus K Q vector divided by Q vector absolute value squared. This is the Runge-Lenz vector. One can check that for this Hamiltonian, each of these components is conserved. Okay? And that's an additional SO3 symmetry, well, at least for bound states, it's SO3 symmetry of the of this theory, but it's not a kinematical symmetry. And one can see this very quickly, but we'll do this after the break, when we'll also develop the theory of Killing tensors. So far we talked about Killing vectors, and with Killing vectors, you understand Killing vectors on the base, on the Q manifold, on the Riemannian Q manifold, you understand the kinematical symmetries. And if you want to understand the dynamical symmetries down on the Q manifold, you need Killing tensors. Now the point with this Lenz-Runge vector and so on is, how do you get the idea there is such a thing? And now with our formal definition and our geometry at hand, we have a very simple algorithm that we can develop, and I'll actually derive it, how you can find all kinds of symmetries, not only the kinematical ones, but also the dynamical ones. I think it's called Van Holten's algorithm. So we make a weak assumption. So we mean that means it's not much is lost by making this assumption. And that assumption is that we have a conserved quantity, Q, as said before. That Q depends on the Q's and the P's, and this is a smooth function on the symplectic manifold. But now we'll actually restrict a little bit. It's not any smooth function, but it's a smooth function if you can expand it into a series, and it could be a finite series, but that's of course included, I equals 0 to infinity if you can expand it in terms of the momenta. So if you have coefficients C, capital C, with indices n1 up to ni, so it may carry no index, okay, of coefficients that depend only on the position q, because we're still in the setting where the symplectic manifold is the cotangent bundle of some capital Q. And here you have the p's, Pn1 up to Pni. Okay? And because this is a nice Taylor series, or we want to understand it as such, we write here 1 over I factorial. But that's just convention. Okay? So we assume we can expand in the p's. Now, for the two examples I wrote down, the angular momentum is linear in p, so I can certainly expand it in p. The Runge-Lenz vector is quadratic in p, in highest order it's quadratic. That's also fine, but we allow any series right here. Okay, so it's a mild restriction. Not every smooth function can be written like this, only the Taylor, the analytic ones, the real analytic ones. Okay, so that's the price we pay for this. And now we investigate or study the condition that Q is a symmetry. That means study the condition that the Q with the T plus V, I write the Hamiltonian explicitly like this because that's still the assumption, vanishes. What does this condition that an observable Q like this is actually a symmetry? We're not distinguishing yet between kinematical and dynamical symmetries, that this is a symmetry. Now, we've got to calculate this guy. So let's start here. What does this mean? Well, it means that the Poisson bracket of this one with that one and so on, so it means the Poisson bracket of Q with T plus V is 0. And what is this Poisson bracket? It's dq by dpk, and now comes dt plus v by dq up k minus dq by dq up k dt plus v d by p down k. Okay? So what is this? This equals, so the Q by the pk, so I have the entire series here. I can't start with 0, I need to start with 1 because the 0th component has no p, nothing happens. 1 to infinity, aha, okay. So finally, so now the question is, can I derive order by order? Okay, finally we'll truncate the series, so we'll at this point just do it order by order. Okay, so you could make another point out of this. You could say, well, actually you just mean up to some capital N, and we have later on to find a consistency condition that we can do this, okay? So let's maybe do it like this, then we don't run into mathematical difficulties and we can derive order by order. Now, in order I will produce a factor I because this is symmetric in these guys, because there's every time the same P. There's a symmetry here, and that symmetry is important, and I will get a 1 over I minus 1 factorial in front, and I get Cn1 up to n little I minus 1, and I derive with respect to pk, so one of the p's goes and produces a delta kni. In principle, I have to do this at every point, but because the whole thing is symmetric, I can just do it for the last if I have the right factor here, and then I have the Pn1 up to Pni minus 1, and that's the derivative of this guy. Agreed? Now, the T plus V, well, let's do this in a simple case. I could do this for a metric that depends on the position Q, and that's what we said. We have a general Riemannian metric. For simplicity in deriving this algorithm, let's assume the metric does not depend on the point Q, okay? And And that will simplify the derivation as much as there will only be partial derivatives appearing. If you make the metric dependent on Q, or you allow that, then you have to replace everywhere where we write partial derivatives, you will have to write covariant derivatives that are compatible with the metric. So the Levi-Civita connection you need to use, okay? But let's not go into this. It just gives you more terms. So then the T has no dependence on Q, the T as we chose it, and only the V has a dependence on Q. So what we have here then is dV, or is del K, with respect to the del V by del QK. Okay? So that's the first term. Then comes a minus sign. Now we derive this guy with respect to the Q. That's not such a biggie. That's I equals 0 to n, 1 over I factorial. And now d by dqk of just the coefficients c, n1 to ni, of course still all symmetric, and all the p's remain because nothing happened to them, to p n I, times, now we derive with respect to pk, but we had this quadratic term that gives us a factor of 2 and yields a gkm pm. That's what it does. Everybody happy? That's what's here? I think that is correct. Now, this is, of course, polynomial in the p's, again, and it's supposed to equal to 0, meaning we can now look at every order in P and it must have any order in P vanish separately. That's also clear. Okay. Thus, or now, every order in P must vanish separately, because only then are two polynomials equal. So let's carefully extract the 0th order. So what's the 0th order in P? Do we have a 0th order? We run from I equals 1, right, is from n is up to ni minus 1. Hang on. So these are I minus 1 p's. If I is 1, I have 0 p's. That's a 0th order contribution. So that is 1 over 0 factorial is 1, is c n1. No, the n1. Right. There is 1 left, but I minus 1 goes to 0, so none of the n's are left. The only thing that's left is a k, and that goes with the dv by dqk equals 0. That's the 0th order equation. Now let's write down the 1st order equation to get some familiarity with this. The 1st order one is obviously the one where the I equals 2. So it's 1 over 1 factorial. I equals 2, so I have a Cn1k. There is a Pn1. Well, but that's the factor. We wanted to leave that out. There's 1p, labeled n1. And there is a dv by dqk. dv by dqk. That's this guy. Then there's a minus. Now we come from here. You see, sorry, I wasn't complete. This one has no contribution because there's always 1p. But now this contribution comes in. It's the I equals 0 is a 2, minus 2. Now I have d by dqk. Now here I have a c that's just that. It's just a c because I equals 0. There are none here. And there's a gkm pm, but the pm we, of course, leave out because that's where we want to make the comparison. But in order to do this, I need to call the n, I need to call it n1 because that was the factor of the p up here, and that equals to 0. That's the 1st order equation, and so on. So let's write down, in general, let's write down the nth order. And let's try to be careful. So that means we want to pick up the terms where we have n p's. Well, we have capital N p's if the I is n plus 1 in this first term. So I is n plus 1, so we have 1 over n factorial. I is n plus 1. Then I have C n1 up to n, because n is n plus, I is n plus 1. Then there is another k. That's right. Then come all these p's. And then I have dv by dqk. That's this guy. And from the second term, I want the guys with n p's. Now, there is an extra one here. So I have capital N p's if the I is n minus 1. N minus 1. I is n minus 1. So I get 2 by n minus 1 factorial d by dqk of the C from n1 up to n minus 1 gkm. But again, the p's here were all in this order n. This last one I need to bring into that same order, so I call this n capital N equals 0, and at this point we would have made a mistake. Well, it's not wrong yet, but I need to do something in this equation for it in order for it to be the nth order equation. What did we do? We actually know that this times Pn1 Pnn equals 0, right? That's actually the full thing for all p's. So we say, well, if this is supposed to be true for all p's, this must be 0. Why is this not true? I pointed this out in the last problem class, or second last problem class. Well, because back here, because this is the same p, just different components, but the same p, this is symmetric in n1 to nn. This symmetry will be imposed on the factor, therefore, right, automatically. So we have it here, but this C is symmetric from the beginning. So I should have said, well, I indicated it. They're symmetric anyway, also by the same token. But in the second term, let me put the k behind because the metric is symmetric. It makes a difference whether I write this bracket or not. So only I need to see, whenever I leave something out tensorially that's contracted, I need to check for its symmetries, and I need to check the projection. That's the more general statement, in this case like this. So now I can take them away, but there is the symmetrization bracket is needed. This one is also needed, but it's already there. Okay? So I pointed this out in the problem class. It's a very common mistake. It's a very important observation that this works like that. Right. So we have these derivatives of the C. And now we take this. So obviously all the other order equations fall under the same principle, apart from the 0th one, because that works somewhat differently. Okay? I think the 0th one is not of this type. Okay, anyway, so now we do the following. We take, so they're true for all n, at least greater than 0. Okay? So what do we do now? Well, we'll pull down all these indices on the C. How do we do this? Well, we apply the metric Gn1 m1 up to Gn n G m n. Okay? And so here we have partials. We can pull a flat metric right through the partial and pull down. If we had had a non-flat metric, I already indicated it, I said it before, all the derivatives here would become covariant derivatives, and then the metric pulls through anyway. Covariant derivatives with respect to the metric compatible covariant derivatives. Anyway, we wanted to save us that issue. So what we get then from that, it's equivalent to, oh, and we could multiply by n factorial, because that cancels this factor here. So then we get C m1 to mn up k. The k stays up there. And now I write this derivative del k just means with respect to spatial coordinates. Del kv minus 2n, because n factorial and the 2 and tralala. And here I have del k, spatial derivative. I pull the flat metric straight through. So I get C m1 to mn minus 1. They're certainly pulled down. But also here I pull down the last one. That gives me a delta k mn. But a delta k mn is this one, mn. And I don't forget that I had here the symmetrization. The symmetrization will be inherited down here, so I need a big bracket here. And this big bracket is all important. Equals to 0. So at this point we breathe. That's all nice. And now we see this coefficient here, the first coefficient in this formula. So it's valid for any capital N greater than 0. And you see capital N needs to be greater than 0 because otherwise this has -1 indices. That's not good. Okay? It's really for N greater than 0. This guy here is of order, well, now I mean by a rank, let me call it rank, is of rank capital N plus 1. N plus 1 up here, don't forget it. And this coefficient here, whose derivative we take, whose totally symmetrized derivative we take, is of rank N minus 1. So there's a gap of ranks of 2 between these two. And now I claim if del m1 c m, or del mn, doesn't matter because I totally symmetrize, cm1 to cmn minus 1 symmetrized, if this equals 0, then one can, not one must, but one can consistently set the C m1 to mn's, so I go one further because this has rank n minus 1. I can set the coefficients, the expansion coefficients C, starting with n. Aha, so in order to finish there, I would rather write up to n, and then I can consistently set the coefficients one further in the series. From n plus 1 onwards, I can consistently set them to 0. Well, this is what we did anyway. We said there is a capital N where the series terminates, so it becomes a sum. Well, obviously, that's where the coefficients from n plus 1 onwards are 0. What I need, or where do I stop? So the question is, where do I stop the series? And the answer is, that is the condition. So the claim is, series can stop. And I need to show you that that's true. Series can stop. You can go on, but you don't need to. That's the point. The series can stop if, or you may stop the series. That's better. 1 may stop the series if, so that puts you in the active role, right? One may stop the series if you can find that a coefficient, if the coefficient is such that this derivative totally symmetrized is 0. Okay, why is this the case? Well, let's look at it. So this is the n equation, the equation for order n. Assume we had chosen the equation for one order further. Then there would here be an n plus 1, and there would be here an n. Okay? So this is the n equation. Let's convert it into the n plus 1 equation. That's this one, right? Okay, so now, assume this guy here is 0. That's our assumption. Assume this guy is 0. Then it follows, well, for an arbitrary potential here, it follows that this that goes on 2 steps must be 0. But you can also go one equation back, where this guy that went 2 steps on was the one that appeared here derived. If that's already 0, also the one step on is 0, and all the furthers are 0. I think you need to look at this at home. Okay, yeah? That's not good. There needs to be an n plus 1 right here. And then there needs to be an n plus 1 here. This was badly written anyway. That's right. Okay. So the point is there is a stopping condition, and the stopping condition is this one. And this stopping condition has a name. It's called the generalized killing condition, or the C is called a killing tensor. I said it already. If G, QG, Q is now dangerous. If G is not flat, so if it depends on the Q's in any coordinate system, if G is not flat, same result is obtained, and it's really not more difficult, it's just more writing. Same result is obtained, but with covariant derivative m n plus 1 symmetrized C m1 up to mn symmetrized equals 0. So you replace the partial with a covariant derivative, right? And you see on the potential it doesn't matter because the potential is just a function on the Q space, right? So there you can leave the partial, but here you need the covariant derivative. And such a tensor C, such a tensor C with these many indices is called a killing tensor. And this generalizes, so that's remark A. Remark B is this generalizes the notion of a killing vector. Well, we already had the notion of a killing vector. We said C, which has only one index up, yeah, is a killing vector if the Lie derivative of the metric with respect to G is 0. But if you write out the Lie derivative and you use the covariant derivative of G, you can see that this is the same condition as that if you pull down the index on the killing vector, that this guy is 0. That's the killing condition expressed with the covariant derivative. So this is a killing vector. Well, you make it into covector by the metric, and then you have this. And a killing tensor can now, I don't think it can be written as a Lie derivative. Maybe it can. Anyway, it generalizes this condition. But not for generalization's sake, but because we derived this as the stopping condition for our expansion, right? Now, what do we do with this? Well, there are several things one can observe. Let's go back. So we get consistency conditions. Well, let's try, some more time left. Let's do an example. Let's take the angular momentum, the angular momenta, well, momentum components. These are the q's cross p's in the correct setting. You know how that works. And you know that that means that the ith component of the angular momentum is epsilon ijk qj pk. And I can raise and lower indices at will because I will use a flat metric throughout. Okay? I can do this. And, well, if I now want to get various angular momenta, I could always introduce an axis n around which I rotate. That would be the projection of this operator. So I would put here another ni. That then gives me one rotation operator, well, we don't know that yet, that depends on n. Okay, fine. But this is now one observable because the n I prescribe. I say I want to look at this axis. Right. So if we now look at this, we know this is supposed to be our q, right? We want to find the conditions for when this angular momentum is a conserved quantity. Okay, so we call it our q, and then we see that our q has no zeroth order term in p, but it has a first order term in p, and the first order term is p sub k, well, we always called it n1 in that case, and the coefficient here in front is ni qj epsilon I j up k, but the k is the n1. Okay, this n, yeah, okay, this n is a vector, these are the components, and this is an index n. But you'll cope with this. And this is the coefficient cn1 of q. You see, this coefficient depends on q and is the coefficient of this 1p. So obviously, this is a series that stops. It stops at the next level. So therefore, we know that we need to have that del n2 cn1 must be 0 if the q is to be a conserved quantity. At least we can let it stop there. So we have the stopping condition at the next level. So we have this guy as a stopping condition. Okay. And so that's this level. And then we also have the 0th level. Let me see if this is a stopping condition. So that means we can, the others are anyway greater than that. And then we have the 0th level where we have ck. So it also follows from various points from the 0th condition, which we shouldn't forget because these are only the bigger ends. C up k del k on the potential equals 0. And we know our ck because our ck is ni for an arbitrary direction n qj epsilon ij up n1. Well, that's the k now again. Del k v equal to 0. And this is easily interpreted because ijk, right, because this guy here is the kth component of n cross q vector. The axis cross q is the kth component dotted into the gradient. So this is the gradient of the potential. This needs to be 0. Now, is this the condition? I think it is, because imagine we choose in space, in three-dimensional space, an arbitrary axis. And now we go to an arbitrary point Q, say this one. And now we evaluate n cross q. N, q, that's a vector pointing right at you, but being here. So this vector that points right at you is n cross q. You agree? Now if you go to, say, this point here, where my tip is, so out of the blackboard plane, so you go to this point here, then you have n cross q, then the vector points right down here at this point. So what you get everywhere along here. Here you get a vector pointing to you. There you get a vector pointing away from you. Here you get a vector like this back there, so that's behind that. You get a vector here. You get this guy is a vector field at each point that goes around this n. Is that clear? At point Q, this vector goes around here. So this guy at every Q is a vector field that revolves around the axis I gave. And the requirement is that in the direction of that vector field, the potential do not change. Meaning the potential is invariant under rotations around that axis. And that's exactly what we wanted to have. We have the components, or we have the angular momentum in this direction conserved if around that axis the potential is rotationally invariant. If around every axis is rotationally invariant, if it's a spherical potential, all components of the angular momentum are conserved quantities. Okay? And obviously we got this from here. Now, is this a kinematical or is it a dynamical symmetry? And the point is, it's a kinematical symmetry. And what do we need to do to study this question, whether it's a kinematical symmetry or not? In order to study that symmetry, we need to look at the vector field that's induced by the Q, the Hamiltonian vector field. And that's nothing but the Q with an open slot. But the Q in our case simply consists of a linear term, Cn of Q times Pn. Agree? Linear in P. Could have a zero term, doesn't matter, but it's linear here. So we do the derivative is this by dpk, but this gives you, of course, a ck of Q times d by dqk minus, well, whatever now comes, there comes some term that's non-zero, d by dpk. But now we take we want to check whether the push forward of this xq exists in the first place. Well, in order for it to exist, what's the push forward? Well, these tangent vectors, if you have the bundle and these are the fibers, these tangent vectors are always in the direction of the fibers. These are the d by dp's. And these tangent vectors, d by dq's, they're always in the direction of the base manifold. So you remember that if this vector here comes up as the tangent to a curve and you push the curve down by the pi, tangent vectors go to tangent vectors, so they become zero. But if you push these guys down, so there's no contribution from this extra part here, because the push forward is linear, this here is pushed forward to the zero vector, there's no contribution. What's the push forward of this guy? Well, it's of course just ck of Q d by dqk. That's a vector field down here. And it doesn't matter where in the fiber you are, because the factor no longer depends on the Q. Why? Because it was linear and the bracket eliminated the last remaining P factor. And therefore, it's well defined. If what stands here still depended on the P's, for instance, if this had been quadratic or higher, then you would, for everywhere else you're on the fiber, you will get a different vector field to push down, so you don't get a vector field. It would be multi-valued. So because this exists, that's the first thing, and then we need to check whether this guy actually is a killing vector field of the metric. But that's also obvious because the CK, so that's the first thing, now check that this push forward of the XQ is killing. Well, how do we do this? Well, we need to calculate this condition here. We need to calculate del M C down n equal to 0. Well, but that we already checked. That's true. So in fact, we push it down, and it is killing down there. Hence, this Q that is L of n, is kinematical symmetry. And now you can look at the Lenz-Runge vector that I wrote down before, and you see it's P cross L plus something. But the L is the angular momentum, already has a P. So it's P cross Q cross P, bracket around the last two. You use two epsilons, you eliminate stuff, and you get something quadratic in P. You don't have a chance that the push forward is well defined because this will still depend quadratically. So any observable that depends quadratically or higher on the momenta must be a dynamical observable, and that then gives you, via these various order equations, conditions that need to be satisfied, and that will depend on the potential, whether they are satisfied or not. And only first order in P quantities have a chance of being kinematical symmetries. Okay? So you have a surefire sign that something cannot be a kinematical symmetry if it depends on P higher than linear order. That was the lecture. Thank you very much.